But something that you should all be aware of, obviously there's a transportation course, about a third of civil engineering graduates end up in a transportation or a transportation-related field, working for organizations like MnDOT or consulting firms that consult or contract to MnDOT or local agencies doing transportation, public works types of things. So, why should you be in this course? Well, obviously it's required as civil engineers. If you're a transportation student, this is really important that you're in here because this is a lot of foundational knowledge for transportation engineering. It is not everything that you might need to know about transportation engineering. We do not focus on highway geometric design, which is covered in CE 4201, which is a technical elective. We talk about traffic engineering, but there's a more advanced traffic engineering course that you might take as a senior technical elective. There's a transportation policy and planning course that's also you might take as a technical elective. But obviously this is a really important course if you're interested in transportation. Now, we often divide the civil engineering department into the wets and the dries. Okay? So the people who are interested in water resources and environmental engineering we call the wets because they deal with things that involve water. And the people who are involved in structures and geo and I guess transportation would be dry students. Because we're dealing with things that are not based on water. We don't build buildings out of water or ice, generally. I imagine you could build them out of ice. Water would be a little tricky. And foundations, although they might be built on marshy soils, we're looking for solid things. So, if you're a wet student, why would you be interested in transportation, aside from that it's a required course?
Because when they treat water, when it rains, lands on the roads and runs off the roads, right?
Yeah.
You have to deal with it.
Good answer. We keep you in business because we create lots of problems. Okay, so transportation has this nasty habit of creating water pollution from runoff, air pollution from tailpipes, and so on, that a lot of environmental engineering and to some extent water resources engineering is involved in mitigating or reducing. So without us, there'd be less of you. So understanding how transportation systems create, how travel demand works and where the demands are going to be and how transportation systems create demands and ultimately create what we call negative externalities or pollutants in the environment is an important input to what are you going to do to mitigate them and where you might need to mitigate them. So if you're building a new highway, where do you put the stormwater detention basin? If you're planning a highway system or a transit system for the next 10 or 20 years, there's EPA regulations about air quality that have to be met. And how do we ensure that the region's total level of pollutants are lower? What kinds of travel demand solutions are there that can help with this? So it becomes interdisciplinary in a lot of ways. Now, if you're a dry student, if you're interested in structures or geomechanics, why would you be interested in transportation?
Geomechanics have to build the foundation of the road.
Yep. And?
Structural engineers build bridges.
Structural engineers build bridges. Okay, some of the coolest things that structural engineers build are bridges, and bridges are about transportation. And so if you want to build more bridges, you want there to be more things to have more connections that transportation demands. So one of your biggest clients as a structural engineer is likely to be a DOT, Department of Transportation. You might have read in the papers or virtual papers. Might have seen on the news yesterday, the new span of the Bay Bridge, the east span of the Bay Bridge opened yesterday after many, many years of construction and many, many billions of dollars spent. Okay, well, why is that there? Because the people of Oakland and the East Bay have something to do in San Francisco, and the people in San Francisco want there to be business, want to visit the East Bay for various things. And of course, the last time the bridge was opened in the 1930s, it was not built to modern seismic standards and suffered serious damage in 1989 and wasn't likely to survive a significant earthquake. So they built a replacement that hopefully will. So it's important. Of course, if you're a citizen or a taxpayer, you use transportation all the time, and you might want to understand how these systems work. You don't really hear complaints about water quality. Okay, I'm drinking tap water, it's fine. Okay, I'm not keeling over and dying. It's not taking me an excessively long amount of time to get the water. It's not expensive, which might mean that the water resources people did their job, or the environmental engineers did their job, or maybe their job's a lot easier. I don't know. And I used to say you seldom hear about structures falling down.
Starting date, Wednesday, August 1st, 2007, at 6 hours, 5 minutes, and 38 seconds p.m.
Metro 50 cars got a report about some sort of collapse in the construction zone north of University. 437. And 551, I'll be 10-8 down here. She's out of the way in that triple lane row.
And 224.
West Metro is going to be 1033 at this time. All cars, 50 cars, we have a bridge collapse. The river bridge over the Mississippi River Bridge is down. Metro. 80 Metro. 60 cars being routed also. Tupper, we'll need southbound closed and northbound. Both sides are down. 2500, you copy?
En route 169 and Highway 7.
Tupper, 1806.
Ending date, Wednesday, August 1st, 2007, at 6 hours, 6 minutes, and 53 seconds p.m.
Okay, so that was from the traffic camera on I-35W. Basically, all the cameras on the regional transportation system are hooked into the traffic management center in Roseville, Minnesota, Water's Edge complex at Highway B2 and 36, B2 and Snelling Avenue, just north of 36. And because we have this real-time monitoring system, not just cameras, but there's loop detectors in the road, magnetic loop detectors, which are counting cars, and they're put in the road every lane, every half mile or so on the freeway system, and on every entrance ramp. We have a real-time picture of the transportation system. Okay, so transportation engineering not only deals with designing something that is going to last for 60 or 100 years, like a bridge, like the bridge over the San Francisco Bay. Not only something that takes 10 years to construct, like the replacement for that bridge, but things that are happening in real time. So from the point of the bridge collapse at 6:05 p.m. on August 1st, 2007, within minutes, I-35W from both directions was shut down to incoming traffic, okay? Because we had real-time information that the traffic management people and the police who are working together can see this information visually, not just getting reports from telephone calls. Okay? We also have a lot faster response system now because everybody's carrying one of these. So, the 911, I'm sure, lit up instantaneously at that point. And they can dispatch people, shut down all the entrance ramps, shut down the road. Everyone can know about it. We can have visuals of it. And we can respond in real time to any type of incident, okay, from really spectacular collapses like that to just a disabled vehicle on the side of the road can be responded to. They'll turn if they find out there's a disabled vehicle, either because they see it in their camera or they hear a report about it, they can move their cameras to look at it, see what the situation is, dispatch somebody who can be there in 10 minutes, and that doesn't turn into a significant problem downstream. It doesn't cause secondary crashes. It doesn't cause more congestion than necessary, and so on. So being able to handle all of this is one of the jobs of transportation engineers, and MnDOT has people who are dealing with all time scales, people who are dealing with transportation in real time versus people who are dealing with the planning and deployment of systems. But then the question is, well, why do transportation systems have a lot of complaints? Okay, so water we think works reasonably well. Citizens don't complain about it, but people complain about transportation a lot. Okay, so there's a couple of hypotheses. Okay, one is that transportation engineers are just incompetent. I hope that's not true. But certainly it's possible that if you just had smarter people in the field, all the problems would go away. I think that there's something more fundamental going on, okay? This is a much more social enterprise than any other type of civil engineering, okay? We are dealing with systems where individuals are producing their own transportation, okay? He's driving, he is autonomous, his load on the system is unpredictable, and we can't design, we technically could design, we cannot afford to build systems that could accommodate every potential demand, okay? And so we have the situation of people overloading the system, okay? So you as a citizen, even if you're not a transportation engineer, can work toward their improvement if you think there's too many resources going towards roadways because you think that more should go towards transit or more should go towards bicycles, okay? You show up at public hearings and you testify and you give public officials this information that you believe this, and they accumulate this information from lots of citizens, and things do change over time. It takes a while, but there's a lot more miles of bike lanes striped in the Twin Cities today than there were 10 years ago, and that's because people advocated for that and demanded that resources be spent in that way. There are a lot fewer roads being built in the Twin Cities. Some freeways have been canceled. Some freeways are being torn down. Look at what's happened to Washington Avenue on the West Bank. Been converted into a light rail corridor in a small street from what had been a freeway-sized facility running through West Bank. Why? Because people collectively had a change of opinion about what the best thing to do was. And if that doesn't motivate you, if you know about transportation, you can always entertain your friends at parties and explain why do buses bunch and why do shock waves and congestion occur seemingly out of nowhere. And we'll talk about issues like that over the course of the semester. So, first question, what is transportation? So, talk with a neighbor for 90 seconds or so and try to come up with a definition of what is transportation. And I'll call on people semi-randomly, and you'll tell us your definition, and we'll see if we can converge on solution. Yeah, okay. Be social. Talk to somebody. Turn around. Whatever. That should be good. It's not mechanical aid. You know there shouldn't be anything you have to do. Okay, so who's got a good answer as to what is transportation?
The movement of people or objects from one place to another.
Okay, I like that answer. Okay. Typical textbook answer is, well, transportation is the movement of people and goods. So we say goods instead of objects, but I understand what you're saying. And transportation engineering is about safety and efficiency. Okay, so we want to move them there with a minimal of cost. So this means minimal amount of money expenditures in order to do this, and a minimal amount of time expenditures in order to do this, with a minimal amount of risk. Okay? You could even think of safety as part of efficiency if you wanted to, and say, well, a small probability of resulting in a terrible thing like a crash or an injury or a fatality reduces efficiency. But we normally keep them separate because people don't like monetizing value of life. We do it, but people don't like talking about it that way. So we could have a conversation about why your life is worth $5 million and your life is worth $10 million and your life is worth, something else. And it'd be a very interesting discussion. I'm happy to talk about that in later when we talk about benefit cost analysis. But for now, we'll just say that we treat safety separately from efficiency. Anybody have any other definitions of transportation? Any other goals for transportation? Okay. So, transportation engineer is supposed to design something that is safe and efficient. All right, I'm going to show you another video. This one is not for the meek of heart. Not dead. Okay. Severely injured, of course. This happened. The headline I have is from Dayton. It says, "Doctors revived a man Sunday just hours after medics pronounced him dead on the scene of a car crash." So what went wrong? Somebody ran a red light. Okay. So that was one problem. Both drivers were speeding. I mean, obviously the one who ran the red light was speeding, but was speeding above the speed limit. Pedestrian was wearing headphones, not paying attention. He had the right of way, so it wasn't his fault. You're allowed to walk around with headphones, but he wasn't as observant as he might have been. He didn't pick up that there was this crash until a little bit too late to get out of the way of it. So there's a few things going on here. You can see this is a fairly wide intersection. This is at least 5 lanes wide here in this direction, and it's at least 5 lanes wide in the cross direction. There's hanging traffic lights. It's hard to tell from here. It's not like there's necessarily a sun glare problem. But the driver who was going this way, presumably the one with the red light, because the other cars are stopped there, did not see that this person, he had a red light. And why did he not see he wasn't having a red light? Who knows? The one going across didn't see that this person didn't see that. And you say, well, it's the driver's fault. Okay. So one of the things that we're trying to do in transportation is to get away from the word accident and use the word crash. Because accident implies that people couldn't have done anything about it, they couldn't help it. But crash allows you to assign blame. And certainly there's some blame to go around. Some of the blame certainly goes to the drivers, but is there anything that the transportation engineers could have done? And it's really hard to say from this limited piece of information, but something to think about. Is there anything the transportation engineers could have done that would have helped the drivers do their job better? Okay? And we do those kinds of things all the time. Okay? We could say that we could tell drivers you have to drive 12 feet from centered on 12 feet from the right-hand curb or 18 feet from the right-hand curb, or we could do something a little bit more convenient and paint lanes. We paint lanes. Why do we paint lanes? To help drivers. We help drivers succeed in their task. Why do we put traffic lights in there? To make the system more efficient when it's congested, because the first alternative below that is typically a 4-way stop sign, which requires every driver to stop, and traffic lights only require half of the drivers to stop, and fewer drivers if you coordinate the signals. But there's other designs that are safer than intersections like this, like roundabouts, which we don't use a lot in the United States but are used in other countries, that might very well have prevented something like this because drivers wouldn't have been going so fast into the roundabout, and drivers wouldn't be hitting each other at a T-like right angle intersection, right angle crash. If they were to collide, it would be at a much more modest collision because they would be going almost in the same direction along the roundabout. And one of the things we'll talk about later in the semester is roundabouts. So this is one of the things to think about is what can the transportation engineer do to help drivers and pedestrians and transit users and bicyclists be safer. Okay.
If you hit me at 40 miles an hour, there's around an 80% chance I'll die. Hit me at 30 and there's around an 80% chance I'll live.
Okay, so this is a British public service announcement campaign. And they're asking people to drive 30 miles per hour in residential areas. Okay, so if you hit somebody at 30 miles per hour, there's an 80% chance they'll live. That's great. If you hit them at 20 miles per hour, the chance that they'll live is even higher than that. If you hit them at 5 miles an hour, the chance is even higher than that. And so the question is, where do you make this trade-off between safety and efficiency? If we wanted a perfectly safe system, everyone would be driving around at 1 mile an hour in, well, they would make everybody walk because it's really hard to, not impossible, but it's really hard to kill somebody while you're walking, and you'd be walking at 3 miles an hour. But we're trading off some safety for some efficiency because we want to go faster too. And we've done a very good job of insulating people inside of vehicle cabins. So we have seat belts and we have airbags, and fatality rates in the U.S. have gone way down from their peaks in the 1950s because cars are a lot safer. Okay, so fatalities in the U.S. on the order of 33,000 today. They used to be on the order of 55,000, 60,000 a few decades ago, and there's a lot more miles traveled. So safety's improved significantly, although not as much in the U.S. as in some other countries. But all of those safety improvements within the vehicle do nothing for the people who are outside of the vehicle, like the pedestrian or the bicyclist, and don't do anything for people who are riding other modes of transportation, like mopeds or motorcycles and so on. And what we require within automobiles versus what we require in the rest of the world is a really interesting thing to think about. Why is it that cars, you have to be buckled up and have airbags, and yet you're allowed to ride a motorcycle without a helmet? You know, I mean, there's things like that. Why do these rules exist? And obviously there are answers to these rules, but they're not logical, sensible answers. They're political type of answers. And you're operating in a political context, and it's a very imperfect world. Okay, so So, in this course, there's two major sections. One is on planning and one is on traffic. The first unit we'll talk about is in transportation planning, so we'll be doing that over the next 6 weeks or so. And after that, there'll be a quiz, and that'll talk about the planning process, how are decisions made in the transportation system, forecasting, evaluation, those kinds of things. And then we'll be talking about traffic engineering and operations. So we'll be looking at a more microscale issue of queuing of vehicles, traffic flow on highways, capacity and level of service. And then we'll spend a few lectures talking about transit planning and operations, which transit is obviously different than highway transportation because it's scheduled and because there's basically individuals aren't driving themselves, but they're in vehicles, and the vehicles have to be managed separately. And so there's another layer of transit planning operations, which has some aspects of traffic engineering, some aspects of transportation planning. So in planning, you might recognize this as the Twin Cities metropolitan area. This is how transportation modelers think what the Twin Cities looks like. Okay, so there's a Mississippi River here and Minnesota River down here. You can sort of make it out. And to us, the Mississippi River is an absence of roadways, because otherwise we have a grid system, but then we have this river interrupting it. You can see the dark blue lines, okay, are the freeways, the high capacity, high speed system. And then there's a finer gradation of the system, which are arterials, major arterials. We typically have every mile east-west and every mile north-south. There are major arterials, and this dates back to the days before the Twin Cities was developed, back when it was, agricultural area primarily, back to the survey standards that were set up with the Northwest Ordinance back in the 1780s. And this pattern has just been replicated across the Midwestern and Western part of the United States. And then within that, there are a finer mesh of roads, typically at 1/10 of a mile or 1/12 of a mile or so on, that create the street grid. And when we're modeling at a planning level, at a high level, we're not generally predicting what's happening on every small street. We abstract that. And so we have traffic zones. We'll talk about this more when we talk about forecasting, that replace a lot of the small streets, and this is where origins and demands begin. And so if you've had any electrical engineering or electricity, understand electricity, think of it as sources and sinks. So we're modeling the system as a network form. If you've had any fluids, and you can think of them sources and sinks. I guess the sink, what is a sink? Well, that sink is where all of the water goes down. Okay, well, a sink in transportation is where all the demand goes to. And a source is where it comes from. Okay, the faucet in water metaphor. And before people used computers to model transportation systems, they actually built physical structures of networks and poured water onto these networks and saw where the water leveled out to try to figure out what the relative flow would be on various places, because the idea is basically the same. People have also built transportation networks out of electrical circuits. Now it's much more convenient to do this in software. Okay, so second part of the course, talk about operations and traffic flow theory. We have traffic signals. Okay, so this is, you can see the mountains in the background. These are photos actually from California. We don't have mountains here, sadly. And you can see, well, what's going on. Okay, we've got green light here and no right turn on red arrow here, so you can't make you can't make left turns here. There's 2 left turn lanes. Sometimes they're green, and then you block the opposing traffic. And there's ways of doing this that are standard ways of doing this in order to ensure both safety and efficiency. Okay. There's a controller box. And you see these. You probably don't pay attention to them before, but now you'll see them everywhere. There's controller boxes at all of the intersections. And there's their big electrical cables, okay, that go down this pole, under the pavement, and into this controller box. You'll do a tour of the Traffic Observatory in October, which is a lab that we have on campus. I don't know if they're on a temporary site. I'm not sure if they have a controller box. But if you open this up, you'll just see these big cables coming in. And, it's like something out of technology out of the 1920s or 1930s, because it's a technology out of the 1920s and 1930s. And people are slowly converting this over to a modern system with modern controllers, computer controlled, with software controlled, where you still have to gather up the information because you still need big cables to change this light from green to red in a reliable way. And you probably notice, if you do it, the traffic signals are far more reliable than your typical Windows personal computer. And they're operating in -30-degree temperature, and you're operating in 120-degree temperature, and they're operating with a high degree of regularity. And there are, not that they never fail, but they fail a lot less frequently because they're using a very simple technology. Minneapolis just announced that they've implemented their central controller for all of downtown, so that they've retimed all of the lights, trying to give people green waves, so that if you hit this green light and then you're going at the right speed, at the next intersection you'll also hit a green light. If you're going too fast, you'll hit a red light, and if you're going too slow, you'll also hit a red light. But that way you can keep traffic moving to the benefit of all drivers, and potentially to the benefit of pedestrians, depending on how you've done it. And there's other things going on here. Okay, so you might have autoscope cameras. Okay, now these are cameras that are above traffic lights, and they're counting cars. Okay, so basically the camera is taking a picture of a very specific spot in front in a particular lane, and they can detect, is it pavement, because they know what the background looks like, or is it not pavement, that is there a vehicle over it? And this works really well in most conditions. There's certain lighting conditions where cameras don't work real well, like in the middle of the night, and if somebody's got their lights off and things like that. But this is a way of trying to count traffic, and you can count over a space, not just a single point, but over a space. You can count how many cars there are, and that can tell the traffic signal, should I be red or should I be green? Because if there's a lot of cars here and there's not a lot of cars in the conflicting direction, then you can give a green light and improve efficiency for all concerned. If there's cars still coming, you can extend a green light rather than making them stop. So there's things like that that you can do in order to improve traffic flow. Okay. There's also devices above traffic lights that you might see if you go out to look at the traffic lights in Dinkytown. Little tiny things above it which are designed for emergency vehicles. And the emergency vehicles can press a button inside saying, I'm coming through, and that will hold a green light if they've already got a green light, or will shift it from a red light to a green light as quickly as is safely possible so that the emergency vehicle doesn't have to stop. And as part of a new bus system that Metropolitan Council wants to put out on Snelling Avenue, arterial BRT, arterial bus rapid transit, they want to provide this ability to do some signal preemption or prioritization for transit vehicles as well, so that transit vehicles can go faster. And the reason you'd want transit vehicles to go faster is transit vehicle might be carrying 20 or 50 people, and the car is only carrying one person, so you want to make sure that those 50 people suffer a minimal amount of delay. Okay, so all of these are connected into the controller box. Okay, so this is the inside of one. And, so they'll have a controller box, they'll have a bunch of cables coming into and out of the system. And then we've got issues of transit planning operations. Okay, so how do you schedule buses? How do you not only come up with a schedule and a map of where you want the buses to run, how do you schedule drivers for those buses? How do you operate the system efficiently? So when is travel at peak? What's the morning peak hour? 7:30 to 8:30. Depends on where you are exactly, but say 7:30 to 8:30. When's the afternoon peak hour? 4:30 to 5:30, let's say. Okay. So how many hours separate out 8:30 in the morning from 4:30 in the afternoon? It's 8 hours apart. Okay. How long is a workday? Typically, a workday is 8 hours. So if you have bus drivers and you want to provide a maximum of service in the peak hours, you have to have more bus drivers because people have inconveniently chosen to all work on the same schedule. And your peak, you can either have a bus driver who works 4 hours, takes 4 hours off, and then works 4 hours, which is a really awkward schedule. Or you can have a set of bus drivers for the morning shift and a different set of bus drivers for the afternoon shift. So labor and scheduling is a very difficult issue in transit planning and operations. It's the same kind of problems you see in the airlines with flight crews and pilots and things like that. Different set of work roles, but same kind of problem. It's a scheduled transportation system, and you need to make sure that you have your drivers in place at the right time, in the right place. Okay, the buses will generally start at various bus garages scattered around the region, but it might be more convenient to change drivers somewhere along the route, and so how do you organize that becomes an interesting question. Now, if you're interested in highway design, there's a course for that, CE 4201, and that looks at vehicle performance and geometric design in more detail. Okay, so how do you figure out what is the curvature of the road? How do you figure out on the horizontal? How do you figure out the vertical curvature of the road? when you're building it, you want to minimize cut and fill, you want to minimize the amount of dirt that you have to move, but on the other hand, you don't want the grades to be too steep because vehicles have a hard time going up steep grades, particularly trucks, and you don't want to make them use their brakes too often either. So you're trading off different types of efficiency for the drivers versus efficiency for construction, and those are the kinds of things you need to think about.